In the last video, we looked at dislocation glide and dislocation climb. In this video, we'll look at kinks and jogs in dislocations. What are kinks and jogs in dislocations? Those are steps present in dislocation lines. For kinks, it can be viewed as a subset of jogs. It's a bit confusing. The main difference of a kink and a jog is the step in the kink lies within the slip plane, while the step in the jog usually lies outside the slip plane. Kinks can be usually created through nucleation, while the jogs are usually created via dislocation interaction. You should be already familiar with the kink mechanism in the BCC metals. In BCC metals, the screw dislocations are less mobile, the edge components are more mobile. Assume we have a straight screw dislocation in the BCC metal. To move the entire screw dislocation is very difficult. The easier way is to nucleate those kink pairs on the screw. And the kink pairs will glide away from each other. Using this process, you effectively advance the screw dislocation by one atomic layer. You can also view that in 3D, and these steps represent the energy barrier. For a screw dislocation, it lies on the energy minimum. It is much easier to have a small edge component to go over the energy barrier and then glide to advance the screw dislocation. After looking at the kink mechanism in BCC metals, let's look at how jogs are formed. We will look at two scenarios. In the first case, we have two dislocation lines. They lie perpendicular to each other. Also, the Burgers vectors B1 and B2, they are also perpendicular to each other. Two dislocation lines, XY and AB, where AB is stationary and XY is mobile. XY has a Burgers vector B1 and AB has a Burgers vector B2. Now move XY and let it cut into AB. After the dislocation interaction, XY remains unchanged. But a step is created on the dislocation line AB. The step size is B1 and this step is a jog. Note the step P prime does not lie on the original slip plane anymore, so it is a jog instead of a kink. Let's look at the second scenario. In this case, again, we have two dislocation lines perpendicular to each other, but in this case, the Burgers vectors are parallel to each other. Holding AB still and glide the dislocation XY. After the dislocation interaction, two jogs are created. For the jog on the dislocation line XY, it has a size of B2, which is the Burgers vector of AB. And for the jog on the dislocation AB, it has the size of B1, which is the Burgers vector of XY. After discussing the formation of jogs, let's look at the motion of a dislocation that contains a jog. We start with a screw dislocation, and the screw dislocation contains a jog, P prime. Since the screw dislocation lies on the slip plane, it can just glide on the plane. However, the jog does not lie on the slip plane. In order to make the jog move, it has to climb. Since dislocation glide is much easier than dislocation climb, the jogs are actually slowing down the dislocation motion. And the slip part of the dislocation can actually bow out. In the last video, we learned dislocation climb can only be assisted by diffusion. So a lot of vacancies will be generated in this process. These vacancies can self-organize to form nanoscale dislocation loops. Before wrapping up today's video, we will extend the concept of jogs into superjogs. In the previous examples, the jogs we've been looking at, they are only one Burgers vector in size, so that's usually one atomic plane. For jogs with more than one atomic plane, They are called super jogs. Let's look at 3 cases here. In the first case, it's a regular jog. The dislocation will move, and the jog part will leave behind a lot of dislocation loops. In the second case, you have a super jog, which is super large. Then the jog cannot move anymore, and the dislocations will just glide on their slip planes, leading to the spiral morphology. In the third case, you also have a super jog, but the super jog is small comparing to the second case. In this case, this jog is not really movable. But these two dislocation lines now can interact with each other, and that forms a dislocation dipole. For dislocation dipoles, you have the dislocation lines parallel to each other with the opposite Burgers vector direction. And in the TEM micrograph on the right, which shows the dislocation structure in an iron 3% silicon alloy, you can see dislocation lines are pinched by some features. These are dislocation dipoles caused by superjogs. In the next video, we'll look at a new concept called pyrostress and how the strength of a material can change as a function of deformation rate as well as temperature.